Hello everyone. Today we are going to take a look at how to graph our 6 trig functions. We're going to be looking at them in pairs of sine and cosine, secant and cosecant, and then tangent and cotangent because they are all going to be graphed in similar ways. We're going to look at what the different transformations will look like both in the equations and on the graph. First thing, let's take a look at our sine function written out in its most general form with all of these variables. So we have f of theta is a sine of b theta minus c plus d. And we'll look at what each of those do later on. But our sine and cosine functions, we want to look at where our maximum and minimum values are, which on our standard function is going to be our maximums at 1 and then our minimums at -1 with zeros at 0. It's the same function, just with a horizontal shift of pi over 2. The way that I like to go about graphing these is figure out where our zeros are going to be, or whatever that middle line is, if there's a vertical shift. Find out where your maximum values will be, where your minimum values will be, and then use that to help you gauge where vertically things should be on the graph. Then take a look at your y-intercepts. Cosine has a y-intercept at a maximum, and I like thinking of it as at a maximum, at a 0, at a minimum, because then that's going to be more applicable once we have different transformations going on, whereas sine has a y-intercept at a 0. So there's not too much else with our sine and cosine functions at the start. It just ends up looking like this. Now, when we go to our secant and cosecant functions, the thing is, we know that they are going to be a series of parabolas, and it's going to alternate between concave up and concave down parabolas. Where are the parabolas going to be? It's a little tough to just tell, at least for me, looking at the function and going, all right, wait, what's going on here? Where does this minimum go? Where's the asymptote? So that's why I like to look at it not in a vacuum, but by basing it off of its reciprocal. So secant is the same function as the reciprocal of cosine. So if you graph your cosine function, which we're all most familiar with sine and cosine from previous courses, so if you can graph your cosine function, you can graph your secant function. And just like if you can graph your sine, which you can, then you can graph your cosecant. So let's just quickly graph our cosine function. Okay, so we've got maximum at x equals 0, a 0 at x equal or theta equals pi over 2, minimum at pi, 0 at 3 pi over 2, maximum at 2 pi, and that same pattern where every pi over 2 it's going to switch between a maximum to a 0 to a minimum to a 0 to a maximum, and that's going to continue on. And not let me draw half the line. Yep. Okay, so we've graphed our cosine function. Now, secant is our reciprocal of this. So secant, we want to take the reciprocal of each of these points. We don't need to do that for every single point and look at, all right, well, when theta equals 0, what's the reciprocal? When theta equals pi over 4, what's the reciprocal? And go on from there. The key things we want for these parabolas are to find the vertices, so our maximum and minimum points, and then find out where the asymptotes are. So we look to our cosine function. When cosine is at a maximum or minimum, so for example at theta equals 0, cosine is equal to 1. The reciprocal of 1 is also 1. The same thing happens at the minimums. So at your maximums and minimums for cosine, secant is going to have minimums or maximums. Then, when we take the reciprocal of zeros, like at theta equals pi over 2, cosine of theta is equal to 0. When we take the reciprocal of that, we're dividing by 0. I'm not going to write it down. It's a little too dangerous. But it's going to be undefined. So secant is undefined at these points, and it's an essential discontinuity, which shows on the graph as a vertical asymptote. So everywhere that cosine is equal to 0, then secant is going to have a vertical asymptote. Once you have these maximum and minimum values and your asymptotes, you're ready to graph secant. So we just go through, finish out these parabolas, and this is enough to have an accurate sketch of the graph. We don't have to go through and graph some of these points very specifically, because by hand we're dealing with irrational numbers, and go graph the square root of 2. We're just not going to get it as accurate as we need to, so this is a good enough approximation. So what we can do is, if you would like, you can go through and get rid of your cosine function, and then there is your secant function. It's a series of parabolas alternating between concave up and concave down. Now, for your cosecant function, it would work the same way, just with your sine function. So anywhere that sine is equal to 0, cosecant's going to have a vertical asymptote. And then anywhere that sine has a maximum, your cosecant's going to have a minimum. And you have that single point of overlap on each of these intervals that are between the asymptotes. Okay, so this in, I guess that's silver, is your cosecant function. It's the same as secant, just shifted pi over 2. For our last pair, we're going to look at tangent of theta and cotangent of theta. With these two functions, they're going to be the same sort of shift of the other pairs, where tangent and cotangent are shifted pi over 2 horizontally. However, there's also a reflection over the x-axis. So tangent of theta is going to be a series of cubic-looking functions with asymptotes. So if you can graph a cubic function, you can graph tangent. And I know that that is not the most professional-looking tangent, but did not go to school for art. So the easiest way for me to remember these is to just start substituting some points in. And by some points, I mean start with 0. So tangent of 0 is 0. Tangent of pi over 4 is 1. Tangent of negative pi over 4 is negative 1. So we have that slope of 1 between the center of our little cubic squiggle and the next point as x approaches infinity, and as x approaches negative infinity, going to the left and going to the right. Those next points are going to have that slope of 1, just like your cubic function. Then we look at tangent is equal to tangent of pi over 2 is undefined, because tangent is cosine divided by sine, and then tangent is sine divided by cosine. That's why I paused a minute. So the tangent of pi over 2 is undefined because you have 1 divided by 0. There's going to be an asymptote. So once you have the asymptotes and those 3 points, you can draw a cubic-looking curve for tangent. Now, this is a periodic function just like the others, so it's going to repeat. So every pi, tangent is going to have a 0. Every of our odd pi over 2's, so 3 pi over 2, 5 pi over 2, negative pi over 2, negative 3 pi over 2, and so on, tangent will have a vertical asymptote. So it's going to look just like this. And then you would go through, and I would recommend doing those other points, but I want to make sure that we can get to everything and you not have a 3-hour video. So that's what tangent looks like. Cotangent is going to work in a very similar fashion. So for cotangent, we still want to substitute in a few points, like 0, cotangent of 0, since cotangent's the one that is cosine divided by sine. Cotangent of 0 is undefined, so we see asymptotes at those whole number values of pi. So it's 0 pi, 1 pi, 2 pi, negative pi, and so on. You can draw your asymptotes. Then, for cotangent, halfway between those asymptotes, just as with tangent, there is a 0. If we substitute some points in, like pi over 4, cotangent of pi over 4 is 1. Cotangent of 3 pi over 4 is negative 1. We see this same pattern with the points to either side of the zeros as we did with tangent. Just cotangent is decreasing over its entire domain, whereas tangent was increasing over its entire domain. So this is what cotangent looks like. Same graph, just with a horizontal shift of pi over 2 and a reflection over the y-axis. Now, let's take a look at what our different parts of the equation are going to change on each of these graphs. So we've got a sine of b theta minus c plus d. So let's first talk about a. A is going to change our amplitude for this function. So if we look at our standard sine function, I'm just going to do a quick little sketch here, do a few of the points. It follows this pattern. So I'm connecting the dots. The amplitude is going to affect where the maximum and minimum values are on the y-axis. Nothing changes on the x-axis due to the amplitude. So your zeros still going to be at 0. Your maximums are still going to have the same x-coordinates or theta coordinates, except they are now going to be at the y-coordinate of 2, or just take that amplitude of whatever a is, and that will be your new maximum. The negative version is your new minimum. So same x-coordinates, just different y-coordinates. This is going to be the same for sine and cosine. And then for secant and cosecant, because they are based on sine and cosine, they're going to follow a very similar rule. So for example, let's look at, I forgot to mention that was 2 sine theta. This, let's do 2 cosecant theta. Well, you have the same asymptotes where sine is equal to 0. And then the same where the maximum for sine is your minimum for cosecant. Minimum for sine is your maximum for cosecant. And we have the same pattern with parabolas, just the amplitude makes the parabolas for cosecant and secant farther apart. For tangent and cotangent, it's just going to change the slope. So if you know how to graph your x cubed function, which you do, then you can graph tangent and cotangent with any changes. So if this is tangent of theta, let's look at what happens for 2 tangent of theta. Helps if I write what I would like to write. So your zeros stay the same, your asymptotes stay the same. That 2 is just going to really be our slope here. So we go over pi over 4 up 2, down 2, and then left pi over 4. So we have the same type of curve, just it's going to be a lot steeper if the amplitude is 2, or a little flatter if the amplitude is between 0 and 1. And just as with your standard functions, if a is negative, it's going to cause a reflection over the x-axis. Now, let's take a look at a different change. So let's look at our period change, because really for C and D, we're not going to spend too much time on that, because it's going to work the same with our horizontal shift from C, where like if you have something of sine of theta plus pi, then since it's a positive pi, you're going to go left pi. And just as I went through for all the points, individually you can go, all right, well, we're just going to take this point, shift it over pi. Take this point, shift it over pi, and see the different, the pattern that's going to happen there. But you can take it point by point. If you're having trouble with these, I always recommend just graph your standard sine, cosine, tangent, secant, whatever, and then do the transformations based on that. That's going to help out. D is going to be a vertical shift. So same thing as with your standard functions, like if you have x squared plus 4, it's going to move things up 4. If instead you had sine of theta plus 3, everything is going up 3. B is the probably trickier one for many people with these periodic functions. So say we graph sine. I am partial to sine. It's my favorite. There isn't a right or wrong answer, but as long as you have an answer to what your favorite trig function is, great icebreaker when meeting new people. So there's sine of theta. For sine, cosine, secant, and cosecant, the period of the function is 2 pi divided by b, and then for our tangent and cotangent, the period is pi divided by b. So the period is the time it takes for the function to go through one full cycle, going and repeating itself. So for example, here is one full period for sine. There's a 0, a maximum, another 0, a minimum, and then another 0. So think one full rotation of the circle, just in this case we're starting at 0 going to 2 pi. If you change what your period is, then that's going to either expand or contract your function. So let's take a look at what happens when we have, let's say, sine of 1/2 theta, which could also be written as theta divided by 2. Since b is 1/2, that should kind of stretch the function out. So for our period, I'd like to write out over here. So the period is 2 pi divided by, so 1/2. So our period is going to be 4 pi. So we don't have quite enough room on this graph for here, but we can get some of an idea. What we always want to do when there's a period change is start off with your y-intercept, because if we substitute in 0, well, it doesn't matter that the 1/2 is there. 1/2 multiplied by 0, the product is 0, so sine of 0 is still 0. But that 4 pi means we need to go 4 pi out, so so 4 pi would be over here. So we would take this long for the graph to do one full cycle. So what you can do is then realize for sine, like here, sine takes half a period to go over this peak from a 0 to a maximum to another 0. So halfway through the period, there's going to be a 0. Halfway through that period, there's going to be a maximum. It's going to follow the same pattern as your standard function with the distancing between the points on the function, just it's going to be a little more spread out. And the same thing would happen over as x approaches negative infinity as well. Let's compare that to something like, let's say, sine of 2 theta, where the period is going to be 2 pi divided by b, so the period is just going to be pi. So we have this same sine of 0 is 0, but then it's going to only take pi for the function to hit another 0. So that means halfway in between those, there'll be that middle 0. Then halfway in there, there's the maximum. Halfway between there, there's the minimum. So when b is a larger number, it's going to compress the function, and it's going to take less time or less theta for the function to repeat itself. And if we continued on with the same pattern, it would look like this. And we would do the same as x approaches negative infinity. Now, you can do the same with all of the other trig functions. We will take a look in class at what happens when we have multiple of these transformations, but I hope this was a helpful overview, and please let me know if you have any questions. Have a great day, and thanks for watching.